Okay, so let me begin. We have been looking at some general things so far, and one thing that I talked about last time is what the situation is in the standard model, not in very complete, with all the details and all that, but try to give an idea of, why it might be that baryogenesis is not easy to accomplish in the standard model. And the way I see it is that the first thing is that with the presently measured Higgs mass, people have figured out that the departure from equilibrium is not very strong, right? It's not a first order phase transition, and therefore things happen very smoothly in the standard model during the electroweak phase transition. And a lot of the asymmetry that the ailerons could create will get washed out because the inverse reactions will compete with them, and if you don't go sufficiently out of equilibrium, they will wipe out whatever you generated. And so because of that, and the fact that the CP violation, at least in the quark sector, is smallish in the standard model, these two facts put together will make accomplishing baryogenesis in the standard model difficult. But it is not completely settled, I believe. People still look at the possibility that in the standard model there may be a possibility to explain the BAU, but it's generally believed that it is difficult. And so today we will finish off this set of lectures with some forays into beyond the standard model theories and how easy or how difficult it is to generate the BAU. So firstly, let me just connecting with what we left last time. People ask if it is possible to extend the electroweak sector somehow, let's say couple to the Higgs in some way with some beyond the standard model, and turn the electroweak symmetry breaking into a first order phase transition, right? If you do that, then in a first order phase transition you have bubble nucleation, and so I'll be very sketchy with this thing. I don't want to go into the details because I'm not an expert, first of all, and secondly, it is not easy physics to analyze. It is quite difficult. But a lot of work has been done in this context of electroweak phase transition. Can it be made into a first order? And so you need to extend the standard model sector in some way for the presently measured Higgs mass. And so what if you couple the Higgs to new states? And then you compute the effective potential of the Higgs, including the contribution due to the new states. And if you can arrange it so that the phase transition becomes first order, in other words, you have the possibility of a barrier. So let's say that this is the false vacuum and this is a true vacuum. And if you have a barrier, then you have the possibility that it's a first order phase transition, and you can nucleate bubbles in this early universe phase around the time of the electroweak phase transition, and the bubbles expand. If there is a bubble of true vacuum inside and false vacuum outside, let's say. So if you nucleate such a bubble and it is of a certain critical size, if it is bigger than a critical size, then the bubble will expand. And it will expand and make everything the true vacuum. And if you have many bubbles that are created, or a single bubble. Then when this expands, this front that is moving, the bubble wall, will take this vicinity, the boundary of the wall, will be out of equilibrium. And so there will be a situation where near the boundary of this wall, you could generate a forward reaction at a different rate than a backward reaction, and you may not erase whatever baryon asymmetry you created. So the sphalerons will be active here, fully active in the false vacuum, but not in the true vacuum, because the true vacuum will be in the electroweak broken phase, and the false vacuum will be in the electroweak preserving phase. So this will be the preserving phase, and this will be the broken phase. And so this is really what I am writing is the Higgs wave and the effective potential here, right? Where you can think of it as a free energy also. So here you have a non-zero Higgs wave, and therefore massive W's and Z's. And so the sphalerons, here you have massive W's and Z's. Sphalerons are not active or very severely suppressed, but here they are unsuppressed. So you can have a lot of lepton number and baryon number creation here, which then gets frozen in when it gets transferred into the bubble. So this is generally the situation that people have looked at, and a lot of work has been done there. And I don't have time to also include that, but I'll just leave you with this possibility that if you can make the Higgs electroweak symmetry breaking into a first order phase transition, then there is many works have shown that you can generate the required baryon asymmetry of the universe. So this, if you want more details, let me just, there is, the classic paper is by, one of the, Cohen, Kaplan. You can look at that paper for, like what I just told you about. They work it out in a lot more detail and ask, can you generate the required baryon asymmetry? Okay, so that is one thing that I wanted to at least just mention, if not go into any detail. Any questions about that before I move on to, I'll mainly talk about leptogenesis and what I call as direct baryogenesis, and just leave this at that. Okay. So this is 1990 and 91. Okay, so let me talk about this idea of leptogenesis, which is extremely popular because of its simplicity in how you can analyze the theory more straightforwardly. And before I talk about it, let me make one general statement about CP violation. What we have said, Sakharov conditions need CP violation, but you can say in a little bit generality, what are the conditions required for CP violation? Let's be general. We will see that this one also works in leptogenesis and direct baryogenesis also. And this is the statement that when we compare a rate, so like a CP violation needs a rate for a process and the corresponding antiparticle process to not be the same, right? So that we can then say that, okay, if we are keeping track of baryon number, then this will imply a net baryon number if this condition gets satisfied. That's one of the Sakharov conditions, right? So you see that one requirement or one way to achieve CP violation is by complex couplings. And if you have some process, right, which has some couplings, and let's say that the couplings are Y, and for the conjugate process, let's say this is gamma, and the gamma bar will usually conjugate. Some couplings will be conjugated in the antiparticle process. You can easily see that by writing Feynman diagrams, right? It's quite clear to us this always happens. We'll see explicitly in leptogenesis an example of what this is, what I'm talking about. But this probably you already know that, it's like there will be various couplings, and in a corresponding antiparticle process, the couplings will get conjugated. The problem is usually if you just, if you look at some random process, it is quite possible that in doing this amplitude mod squared, and let's say for the conjugate process, if this one is, let's say this phase in this coupling is some phi. In other words, Y is some magnitude and phase. Let's just say that the phase in this coupling is thing. Usually you will get this thing to be, and here in the conjugate process, if it is Y conjugated, then this will look like some, let's say A naught. Right. So the couplings will conjugate, no doubt, right? But if when you take the mod squared, this will be the same, right? Even though there is a possibility with complex couplings of a CP violation, every process need not be asymmetric between particle process and antiparticle process. That's because of this thing. When you take the mod square, this just becomes A0 squared. The magnitude, this is also A0 squared. Which is why it is common knowledge that in order to see a non-zero CP violation, you need the interference between two amplitudes, right? Usually, in any CP violating process, it is the interference of a tree process and a loop process. The total amplitude, let's say the tree process is A naught, and the loop process, if we do it at one loop or something, or I'll just call the loop process as A1, right? So now when you have the possibility of interference, then the conjugate amplitude, I can write it as A naught. I will just assume that the tree level process has no phase for simplicity. It could, but that can be pulled out and it will not really contribute anything. So here let's write it as some magnitude times the phase. It will look like that. So now this is in better shape because now I have the interference of two amplitudes. And when I take the mod square, there is a chance that when I compare these two for the rate versus conjugate process rate, there is a possibility that it will be non-zero. But you can convince yourself, even in this case, even though there are two amplitudes, if you compute this, you can do this as a simple exercise. You will find that these two are the same. In other words, the rate as asymmetry, which is gamma minus gamma bar, equal to 0, even in that case. Right? It does better, but still CP violation fails. And this is also common knowledge that this is what is called as a weak phase. This is This is all the terminology that has come about because of the kaon physics or B-Meson physics, right? So because those are all weak decays and we are looking at CP violation in the standard model in weak decays. So anything that conjugates from a process to a conjugate process is called as a weak phase. So a weak phase is necessary for CP violation to happen. You need a conjugation of some phase. Just real couplings, you will never get CP violation. Yeah? So a weak phase is necessary. But as we see from this exercise, it is not sufficient for CP violation. There is something else that also has to happen. And that something else is what is called usually as a strong phase. There is another phase which is required. And that is what is called as a strong phase. Here, when we are looking at CP violation due to weak interactions, the strong phase is referring to phases due to strong interactions, like QCD, right? There could be, some QCD corrections that you will do to the weak process, and that can induce a phase in the amplitude. That strong phase is of the kind which is not simply like that, but it will I will just write it in the same thing. This will introduce an extra phase into the amplitude. But it is a strong phase because it is the same sign for the particle process and the antiparticle process, right? It doesn't flip. And we must have that kind of a phase. If you only have a single phase which flips, you can quite easily show that it will lead to the same rate. But if you also have a strong phase due to some other sector which treats the particle and antiparticle process the same, it should be blind to this conjugation, a QCD of this kind, right? So if you have the possibility that some other phase is introduced which is blind to whether it is a process or a conjugate process, then you will end up with this kind of a situation. Now you do the same exercise, compare this, and you will find that now it is not the same because of the presence of these two phases. I will not work it out, I will just leave that as an exercise to you. It is quite easy to to show that just take this form, compute the mod square. It is pretty trivial to see that in the end you will get something that is proportional to sine phi and also sine delta. So both non-zero is then required. So only one of them being non-zero is not sufficient.
So this strong phase can be seen as a CP conserving phase, or how do you see that?
Yeah, I would think so, yeah. Because it does not conjugate under process to conjugate process, so I would say it is conserving, yeah. Any other questions? So this is a very general aspect of CP violation, independent of what process you are looking at, what model, what theory, right? Believe this aspect must be there in order to have the possibility of a non-zero rate asymmetry.
So here it seems that it's CP conservation which is actually giving you the asymmetry probably.
No, it's neither one, right? I mean, in the end, it is both.
Right.
If you don't have the possibility of a weak phase.
Right, CP asymmetry is there, sorry, CP
right.
violation is there.
Correct.
But from the argument, it seems it's actually, became manifest only this
exactly.
strong phase which...
Yeah, that is a good way of putting it. It became manifest only because there is this possibility of a rescattering phase.
Okay.
Otherwise, that process will not really show a difference. Although it has a potential to show, not every process will be different.
Okay.
Some process somewhere will be different because there will be this phase in some process, right?
Right.
Yeah.
So why did you put this both places plus sign for the strong phase?
That is, I am not explaining that. It is just you compute the scattering phase due to strong interactions between a process and a conjugate process. It will give you the same rescattering phase. If it is of that kind, then it will act like a strong phase.
Okay.
It's kind of a circular, it's a tautology what I'm saying, like in this context, in weak interaction CP violation, you can do the strong interaction corrections and you can notice that, or you can measure it from experiment. These are usually measured from experiment because we cannot compute it. It's a non-perturbative correction. We cannot compute it. So we extract it from experiment, and then you can, I don't know how much you can argue from fundamental principles. From the CP invariance of QCD, you can perhaps just argue that this has to be the same for process versus conjugate process, right? Yeah. If we are not looking at the theta QCD, right? If we set that equal to 0, then perhaps you can use the argument of the CP invariance of strong interactions to argue that.
If your processes have non-anomalous currents, then one can, this is like a phase which is not anomalous, it's like a
Okay.
vector kind of transformation. Of course,
This,
we are
I
not
don't know if
looking
it is
at
this is not like a transformation, it's not like a symmetry transformation.
yeah.
But I'm just saying that, if in quantum mechanics, if you have a scattering, there is some scattering phase in phase shift in the amplitude. So this phase shift, the argument is, if you're looking at a weak process which is conjugated, right? And if you look at the scattering phase shift due to QCD corrections, the statement is that you will have the same phase shift for the process versus conjugate process.
No, because here these phases are coming because of the couplings, right?
No,
No?
no. It's because of rescattering, final state rescattering, for instance. The phase is due to the coupling conjugates. This phase is due to the coupling. It is in this, whatever I guess I erased it, but here. So some coupling Y, when it conjugates, you will get the antiparticle process is going to be sensitive to this coupling. And that is what we call it as a weak phase. But here the phase due to the coupling is what is that phi. But phi, the phase due to rescattering is that delta. If it's a QCD rescattering kind of thing. We'll see another way of getting, let me just point out another way of getting a strong phase
So
like
this is
behavior.
at the amplitude level, so I was not
Yes.
understanding this rescattering term. So
Okay. I'm not sure. Yeah, maybe we
Because-
should think about it. Yeah.
then I could have.
Well, it's not really like phase space, it's really in the
It's
amplitude.
amplitude, yeah.
It's a rescattering in the amplitude. Yeah. It's not in phase space. Yeah. Well, so let me give this thing, and maybe that might give another example of where this kind of a phase comes from. That's this thing where that kind of a phase can arise when you have intermediate particles that go on shell. So if you have some process, like let's say some loop process, let's say, which is of this kind, right? Two intermediate particles, a loop, right? And if it is possible that the masses of these particles are such that these particles can go on shell, if the masses are lighter than this particle, then these particles can go on shell. Or you can look at scattering, right? You can look at 2 to 2 scattering with something where these particles can go on shell. If they can go on shell, then I can cut this kind of a diagram, right? And when you make a cut, you will get an extra I in the amplitude. You just use the Katkowski rules and put those propagators on shell. You will get an extra I due to the cut propagator. So Katkowski rule says p squared minus m squared. You replace by 2 pi I delta of p squared minus m squared. Right? This is what it means to cut a propagator. And then you have to do the full thing. If there are two particles, you cut both of them and then you Wick rotate, do all of it. And you will in the end find that if the intermediate particles can go on shell, you will get an extra I, right? And now if you compare it to the conjugate process, where now all fields are now, let's say this is some phi 1, phi 2. Now this is, let's say, capital Phi. Here if I do it for the conjugate process, right? If I conjugate everything and cut this one, if there is a coupling here, these couplings conjugate. I'm being very symbolic, but in actual thing you will see this working if you do it in a particular theory. But this phase due to the cut, the same thing will apply. So you will get the same I, right? So that extra I, which is a phase of pi by 2, I is just, right? This strong phase like behavior will come due to this I, right? Which is the same for the process and conjugate process, right? You have these weak phases due to the coupling conjugated, but then intermediate particles going on shell will contribute an extra I, which will be the same for the process and conjugate process. Now this was recognized way back. It is pretty standard knowledge in this business, and so that is another place to see a behavior where that either could be due to rescattering or due to intermediate particles going on shell. So this one is satisfies this condition that you have something where there is one phase that flips and one phase that stays the same. And we can apply this in leptogenesis, and it is applied in leptogenesis in the
thermal
intermediate
field
part.
theory, non-equilibrium also, the propagators have this piece which is this normal
Okay.
off-shell propagator, plus there is a on-shell due to the production of real particles on the heat bath.
Okay.
So can
And
this
that comes from an I or what? That
Yeah.
which comes from an I. Okay.
I times
Yeah.
the distribution function times the delta function.
Okay.
So can that be also on one source if this is in the heat?
Yeah, I'm not sure. I've not thought about it. Yeah.
It's in-
Yeah, maybe one can think about that if that can act as a strong phase. Yeah. Okay. Yeah.
In real-time dynamics, you have in the real-time dynamics, you have the propagator, thermal propagator as 1 by p square minus m square, the zero temperature piece, plus 2 pi I times the distribution function that comes due to the particle production, real particle production in contact with the heat bath. I was wondering whether that can be applied here. No, sorry.
Yeah, it is a very general requirement for us that we just need one thing that doesn't flip between process and conjugate process. If that is the case, then we just term it as a strong phase, and any source of that is fine for us, right? But it has to happen at the amplitude level before you take the mod squared. Yeah, that's our only requirement. Yeah. Sorry, I cannot hear you.
In this case, you got the iota, the strong phase, by the cut. How is it related to QCD then?
You could either take that literally that there are light particles in QCD like pions or something which go on shell, or light quarks which go on shell and give you that phase. Or you can think of it as more like a quantum mechanical rescattering phase, either way, right? And so this is why I was not relating this to necessarily the QCD strong phase, but I was just saying that this is one example where you have this strong phase-like behavior, where there is a phase which doesn't conjugate between process and conjugate process, right? Whether you can literally make that in every single case as a rescattering phase to be of this kind, I'm not sure, perhaps not. Okay, let me move on. Yeah, if it is urgent, you ask, otherwise we'll talk later. Or quickly ask, I'll just quickly ask and
So why do we take interference up to one loop? I mean, why not, let's say, increase the loop orders?
you could do it, but usually every loop, is suppressed if the couplings are not very big. If perturbation theory is working, then every loop order is suppressed. So if you compute the two-loop correction, you will get a suppressed contribution,
So
right?
these statements hold that we need both phases. We need
Yeah.
one phase to conjugate.
That's
one
right.
phase.
Here, this thing is made like you can say that this is independent of any loop and all that. This I was making a general remark that there is something which is of this kind, there is something which is of this kind which carries some phases and all that. There must be something like this that goes on somewhere, right? And we can easily see it working when you have one loop. So it is more general than just one loop, two loop, whatever. Somewhere you should have that behavior is all that is required. It's pretty simple, right? All that you say, you must have this thing not equal to this one. What are all the necessary conditions for that? You can work out. Yeah. Okay, let me move on and we will see this thing working in leptogenesis. So this is continuing our, like examples of BSM theories. So here, for classic reference on this, you can look at and this was year is what? 1986. And the idea here is neutrinos have mass, so we can give the neutrinos a mass by the Yukawa couplings and the Majorana mass for the neutrino. So let me just write it as what is my definition of Y? So here is star. I'll not be too, detailed and strict about the SU2 indices and all that. This means an antisymmetric product, but let's gloss over all that and just look at the main point. This is the Hermitian conjugate piece, right? And this is the Yukawa couplings for the active neutrinos. And with the singlet, the right-handed neutrino, which I call N here. So in here is my notation that this is the right-handed neutrino. And we can add a Majorana mass for this neutrino, right? So this line alone, if I only have this line, if I shut off the Majorana masses, then lepton number will be a good symmetry and I can make the assignment of the right-handed neutrino to be +1, the lepton number. That will be a good symmetry, classical symmetry. Of course, it's anomalous, we know that and all that, but it's a good classical symmetry. But if I also write down this one, this breaks lepton number. So this is a key point in leptogenesis, that we add the Majorana masses for the neutrinos and that will be the source of lepton number violation in this theory. So now, coupled with the sphelerons, which I will talk about after I finish giving you this the content of this thing, the sphelerons will then convert lepton number to baryon number, right, at the electroweak phase transition. But let's just keep that thought aside for now, and let's just proceed with this thing to see what really happens. And what happens is, when we look at some processes in this theory involving the right-handed neutrino, we can generate net lepton number, because this theory breaks lepton number. It will not care about lepton number, and so it has a possibility that it will generate a net lepton number starting from 0 lepton number. Yeah? So you first show that as the universe cools, you can generate a net lepton number. So that will be our first goal, and then we will use the sphelerons to turn that lepton number to baryon number. So that is the idea of leptogenesis. So which kind of a process must you look at to argue that there is a net lepton number, right? So again, from the Sakharov conditions, we need a CP violating process. So for the CP violating process, we will look at the right-handed neutrino decay. So let's look at this N goes to L, and then Higgs, right? I'll be symbolic. You can look at electron or the neutrino or whatever, right? We really want to look at the Higgs and a neutrino, right? I mean, that is one physical way of looking at it. Or you will have to look at the W process. But let's be symbolic. We'll not worry too much about completing exactly this thing. So to this, we can add a loop process, because from the arguments that were just made, with just the tree level process, it's not possible to generate a CP violating effect. So we need to add loop processes. So for that, we will add this kind of a loop process. Here from, I know that if I have to have any chance of getting lepton number violation, right, I must invoke the neutrino Majorana, because if I don't invoke this, then it is like it is only going to look at the lepton number preserving sector, and you will never get any net lepton number. So this one I will denote the Majorana mass with a cross. So here N, N. And this one is this Mi, right? This vortex, I can say, has things like here, okay, let's look at this one, L, N, H, right? Let me say that this one is like this. And to say that this breaks lepton number, I'll use this notation, that the arrows don't match up, and so that is going to tell me that this particular thing breaks lepton number. The fermion number is not a good symmetry here, and that's what a Majorana mass does to you. And so here, if I have to have any chance of this lepton number getting violated, I should look at a process where I put a Majorana mass of this kind. So here I want this, right? And another loop diagram that I can look at is of this kind. This will be the H, this will be the LJ, and this will be the Ni. And again, a Majorana mass insertion here. Let's just call this as the kth type, and here will be the kth type. That I will be some number for, if you want the usual models, you usually assume 3 right-handed neutrinos, that I will be 1, 2, 3, the 3 generations of right-handed neutrinos. Although you don't have to have 3, but that's a common choice. And so this will be my H, and this will be the L. So if you look at the structure of the loop contributions here, and I will invoke that strong phase thing by saying that these intermediate particles can be cut, right? Here the H and the L, because they are light states, the canonical seesaw right-handed neutrino is at a very heavy scale, like 10 to the 11 GeV or 10 to the 12 GeV or something. Whereas the leptons and Higgs are all very light. They are at the electroweak scale, the Higgs is at the electroweak scale, and the leptons are much lighter and so on. So these things can go on shell. And so you will get that extra I that I was talking about. That will give you the strong phase in these processes. And these couplings, you can just work out. I will not do it slowly here. I will just write down what these couplings will look like, right? This will be Ij, and there will be some, this is if it is the Lth type and the Kth type. Sorry for this notation. This is just Ij, Kl are my counting, 1, 2, 3, those indices. This really means a charged lepton. So this will be Y, Il star, Ykl, Ykj. You can just check that these couplings are as written down here. And similarly for this one is YIL star, YKL, and then YKJ. So now I have to add these amplitudes and take the mod squared, and with this factor of I coming from this cut in the loop, and then you can convince yourself, I'm not going to go through the full calculations, it's just algebra from here, you just write down all of the things, and you will have to compute this loop, right? There will be some loop integral that we have to do, and you do all of this. You can look at this paper for the details. So you will realize that because of the presence of this thing, you see here what crucially happened is that there was no star. There is a Y and a Y here. Two couplings which don't conjugate themselves, right? So there will be a phase that survives because of that, right? Otherwise, if you had this coupling and the conjugate of its coupling, there will be no weak phase in the amplitude in the end. You will just get 0. So some crucial things will happen, and it is constructed, or we have picked out one contribution which survives when you take the difference between process and conjugate process. There will be many diagrams that you can draw, many processes, but you take the difference between process and conjugate process, they will all give you 0, right? But only certain contributions or certain processes will have contributions where this thing will survive. And this is one such example of it that I have picked, right? And so now you write this, and you will, you can compute the rate. I will not go through all of this. So you will find, let's say this is the I to j. Process and conjugate process. Here conjugate process means N to L conjugate and H, right? That will be the conjugate process. I am going to compare the rates for these two. And you will find that also including the I due to this strong phase, you will find that this will look like imaginary part. Let me take this contribution as an example. And the conjugate of this, of that and I sum over all of the K and L intermediate states. This is supposed to be my L. And you will get, due to this one, you will get an MK, and then there will be some loop integral and loop functions that you will do and all that, which I won't bother writing. So that will be the form of this thing. And the exercise that you, or I leave to you, is to show that this one imaginary phase can be non-zero, or this imaginary part can be non-zero. In other words, this thing should not be real. So if you take more than one flavor of the right-handed neutrino, I believe you can get this to be non-zero, which is what was shown in that paper there. So now you have, because of this I, something that survives, and you will pick up the imaginary piece, and then you have a combination which has a non-zero imaginary piece. And this then tells you that in this theory, you can have a difference in the rate between process and conjugate process. So if I compare, just give me 1 second.
Yeah.
So I'm comparing Ni Lj conjugate rate, rate for these two things. And that's what I call as the mod squared of this entire thing, right? Will be gamma, and then I conjugate everything, and then that will be the gamma bar, and then I'm taking the difference. And the claim is that then you will get some combination that looks like that. And here I've kept only the interference term, right? I mean, the subleading term is this diagram squared, but because this is already one loop, this is small compared to this one. And so I've dropped the second order term, and at leading order, you will get a result that looks like that, which is due to the interference term. And I will leave all of this, the algebra as an exercise. Sorry, Indu, you had a comment?
The second diagram and the third diagram have the mass insertions in different places. Is it critical, or one is inside the loop and the other is outside the loop? Does it matter? I mean,
So here this is for this one, this is a charged lepton. So I cannot put I'm only keeping track of something which breaks lepton number. So here my arrows are saying lepton number, right? This line cannot break lepton number because it has charge. If it breaks fermion number, then I break electromagnetic charge. Yes. Yeah. So I've been very sloppy here. So if you mean really a neutrino here, an active neutrino, then I am writing in what is called as a mass insertion approximation, where then this is a pure active neutrino which does not break any lepton number, and only the Majorana mass is separately. This is before diagonalizing. If I diagonalize, then I guess that is where you are asking this question. Then there are different ways of writing. If I have a neutrino, then I can put a mass insertion there and so on. But in the end, this should be a good guide to how those things will behave also, right? Yeah. So I will leave it at this, that the exercise then is to take this thing and show that this combination here for certain number of right-handed neutrinos and all that is non-zero. Okay, any questions about this? So this one is a way to generate non-zero lepton number. Now after this, what we would do is that because we are going to imagine that this process is happening in the early universe, we would fold in the thermal spectrum of all of these particles, right? The neutrino, whenever it is present in the early universe, will have some thermal distribution function. So I will have to thermally average this thing. And then that will give me this thing. So what I can do is to look at all flavors of N going to all flavors of L, right? I could sum over, first I could just sum over all of this. So let me just say gamma I'm also going to sum over I and j of this delta ij. That will be the total lepton number that's generated in all of the processes, right? And then I could thermally average this thing. Right, to get the thermally averaged rate. And in leptogenesis, where the asymmetry is being generated is in a decay process. It's in the decay of this heavy right-handed neutrino, right? And in canonical seesaw, how many of you know seesaw, canonical seesaw? Neutrino mass generation by seesaw. Rough idea of how it works. Okay, too bad, right? Okay, I don't have too much time to explain, but I will just tell you that this exact same setup is what is used to understand why it is that the neutrinos are so light, right? The way to understand why the neutrino is light, hopefully you know that the active neutrinos, the heaviest among them is of the order of 0.01 eV, which is what, 10 to the minus 11 GeV, right? It's a very, very light mass. So why is it that there is this particle which has this kind of a tiny mass? This model neatly explains why that is, and this is called as seesaw, type 1 seesaw. In here, if you work out the consequences of this theory, you diagonalize the masses and work out what will be the neutrino masses, you will find that m nu is given by this L, whatever is the coupling y, times V divided by the mass, this Majorana mass. And so here you will get that, you will get this relation, right? This m nu is what is measured in experiments, not the absolute value, but mass differences are measured. The biggest mass difference is of this order. So we will just say for now that the masses are of that order. So if you have this mass which has to come out as 0.01 eV, V here is the electroweak wave, which is 246 GeV. Now why, if I say some coupling like 0.1 or whatever, it's like a not too tiny coupling, 0.1 or 1 or whatever you wish to take, V is 246 GeV. If I want this to come out as 0.01 eV, this has to be very, very heavy. M is of the order of 10 to the 13 GeV or something like that. If I take a very heavy right-handed neutrino, then it naturally explains why it is that the observed neutrinos are very light, and that is called type 1 seesaw. It is called seesaw because this is becoming very heavy, right? I mean, this mass, it's like this big mass is sitting here and the light mass is, this is supposed to be a seesaw, right? So it has made this very light by this heavy mass sitting here. So that's why it is called a seesaw. And it's a very nice explanation for why the measured neutrinos are very light. And the nice thing is leptogenesis takes the exact same model for what explains the lightness of the neutrinos and makes lepton number to work, non-zero lepton number. And so that is the appeal of this model, that since we anyway are going to do this for explaining the lightness of the neutrinos, it also ends up giving the non-zero lepton number. So now the point was that because this is such a heavy mass, right, the time when these decays happen is when the temperatures are of that order. So it's a very high temperature in canonical leptogenesis. This physics of lepton number generation is happening at incredibly high temperatures in the early universe. And there is where you would then, to make it work, then what I would do is to take these rates, right, and compare that with the Hubble expansion rate at temperatures of around 10 to the 13 GeV, right? And then I have to show that in the Boltzmann equation that this works out, that given the expansion of the universe, whatever value it has at temperature of 10 to the 13 GeV. How does it compare with the decay rate, right, that we have computed? And then the difference of the decay rate between process and conjugate process. I have to then solve the Boltzmann equation with these ingredients, and that's what is done in this paper. The estimate of that you can look up there. And you will find that for these kinds of masses, indeed, the lepton number that's generated is of the order of what is required to match the observed asymmetry. But right now, what happened is at 10 to the 13 GeV, you only generated lepton number. Baryon number still continues to be 0 here because we never, this thing is only about the lepton sector, right? Baryons are sitting separately. They don't talk to each other here, right? So you have a situation where you have, after this process completes and the temperature drops below 10 to the 13 GeV, and then the neutrinos, right-handed neutrinos have all decayed away, it has generated some lepton number. The net baryon number is 0, and there is some initial lepton number that all of this generated. So that will be the situation in the universe after the right-handed neutrinos have all decayed and gone away, right? As the temperature drops, these guys become Boltzmann suppressed, and the inverse reaction shuts off, right? And that is the way that out of equilibrium condition is being met here, right? If when the temperature drops below the mass of the right-handed neutrino, the inverse reaction is becoming disfavored because of Boltzmann suppression. So that is a way of evading thermal equilibrium conditions. So you can go one way but not the other way. And that is how this one gets that out of equilibrium condition, but one of the things that was in the Sakharov condition. And CP violation, as we said, is by these complex couplings, and then the strong phase due to the intermediate particles go on shell. And what was the other one? Lepton number violation. Lepton number violation or baryon number violation, that comes from the Majorana mass for the neutrino. So all three Sakharov conditions are here, and we explicitly have seen one example of how all of these go into this kind of a model. And this is a nice example where it is not very complicated to keep track of, right? We can just keep track of all of this and see how it is working. And just the last point before I finish this topic is to then say that, okay, having generated this lepton number, now when the temperature cools to where the electroweak phase transition happens, there the sphalerons, or even above the electroweak phase transition scale, the sphalerons, what they are doing is, there is this paper by, I don't have time to explain, but there is this classic paper by Kuzmin. You can look at that paper. It's so I had the year written down somewhere here. 1985. So in this paper, they argued that what the sphalerons do is to drive B plus L to 0. So the electroweak sphalerons will drive any B plus L to 0, but leave B minus L untouched, right? Because that's conserved in these. We argued that B minus L has no anomaly. Only the B and L have the anomaly, and the B plus L combination is anomalous, but the B minus L combination is not anomalous in the standard model. So using these facts, they showed that you can just set it up in the Boltzmann equation and you will find that the final B that you get after the sphelerons do their thing the B plus L decay away, right? And then the B minus L is whatever you started with, half of that is in baryons, and the final leptons is going to be minus baryon number, right? So that will be the situation after the sphelerons are active. And post electroweak phase transition, as the temperature cools below the electroweak scale, then you have generated both baryon number and lepton number, which is what we need to match the observed universe, right? We have both lepton number and baryon number now. And so you generate all these baryons also with a net baryon number in the post electroweak phase transition. And so that is how leptogenesis works. Questions? Probably very quick, but I've given you the essential points here. Yeah, after the electroweak, after the sphelerons shut off and go away and do everything and so on. When they are active, you can show that this is how it behaves. So as time progresses, B plus L exponentially drops, right? This is a solution of the Boltzmann equation. And then they exponentially decay away, B plus L. And then B minus L will be conserved, and so you will get half of what you started out with. Because here you generated only lepton, right? So B minus L is really minus L in initially, right? After the leptogenesis ended, you have this situation. Whatever leptogenesis, let me write it this way. Whatever this lepton number got created in leptogenesis, that will be, minus of that will be the initial B minus L, which is conserved by sphelerons. So then you just, it is easy to convince yourself that B plus L should be driven to 0, right? And then B minus L should be whatever you started out with, and whatever solution, I think it will look something like that. But yeah, there will be both lepton number and baryon number which will be non-zero, because one of them is conserved. If B minus L were not conserved, both could have been driven to 0, right? And that would be useless for us. But because B minus L is conserved in sphelerons, then you will end up with a non-zero B and L. Okay, so in the last 10 minutes, what I will do is to just tell you quickly about another model, and that will be the last of my BSM models of how to generate the baryon asymmetry. Yeah.
Phase transition to be first order.
No,
It's
yeah.
already generated
That's
earlier,
right.
and then
That's right.
only the electroweak phase transition comes to remove away this last term,
Yeah.
E plus L term.
What is bad for us in baryon number generation in the standard model? The problem is that it is all driving B plus L to 0. It is erasing everything. Here it is used to advantage. The fact that it is erasing everything is meaning that it is transferring from lepton number to baryon number and so on, because this is conserved, whereas this one is driven to 0, right? So yeah, as you rightly said, here we don't care what kind of a transition it is. We just want it to be active, that's all. Sphelerons have to be active. Yeah. Otherwise, you will end up in a situation where you only have lepton number and no baryon number, right? And that's not going to match observation. So that's why this is invoked, that you generate lepton number, but then you transfer some part of it into baryon. So last thing, very quickly, I will tell you about what I will call direct baryogenesis. This is my work with Rakesh Tibrewala, and this was, I'll write down the archive numbers. One three two three one. So what we did in these three papers is to show that if you look at a theory where you have some chi, now what is taking the place of that n is this chi. So we'll make this chi as Majorana fermion. With its Majorana mass, let's say m chi or m, let's say, right? And then if this chi has interactions where it decays or has interactions with 3 quarks, let's just call this as Q, Q, Q. Or if this is going to confuse, let me be more specific, right? So this is quark-like fermions. So there could be a U-type quark and a D-type quark, 2 of them, right? And so this one has quantum numbers of a neutron. If you see that this is like right. And so we just took a situation where there is a 4 fermion interaction of this kind and then asked, since it is Majorana, the same fermion chi can decay now to the conjugate also. Right? And there would be loop processes now which I need for generating CP violation, and let me just sketch how that loop process will look like. So if I have this kind of a thing, then I can write one loop process which looks, let's say, like this one. So this is starting with a chi, and then I'm going to look at the decay of, let's say, chi to u dd and compare it with the conjugate process, right? So for that I will look at contributions like this one has chi to u dd, and this one is that, and I could have this Majorana mass insertion here, which is here, let's say this is chi and this is j, right? I can have this will indeed, like if I start with the Dirac fermion and then add a Majorana mass to it, I will have a theory with 2 Majorana fermions. So I and j are 1 and 2, right? So I can have this kind of a contribution as a loop process to this tree contribution. This will be some tree level process which will give me this thing, and then similarly I will take for the conjugate process, this is a tree diagram and the corresponding thing with conjugate. In fact, this will be conjugate if you just look at how the arrows work and all that. And here the baryon number violation is what is directly happening, because these carry baryon number of 1/3. So 3 quarks put together will be baryon number of 1. So here you are generating baryon number of 1, here you are generating baryon number of -1. And so if the rates for these two processes are different, you will get a baryon asymmetry. And what we do in these 3 papers is to go through in gory detail this theory and then show that CP violation works out. And we have put in baryon number violation by saying that the chi is Majorana. So this chi Majorana mass will break baryon number. So that's one Sakharov conditions that get satisfied. And out of equilibrium condition is again comparison with the Hubble expansion rate, right? So we set up the Boltzmann equation and compute the rates for all of these decay processes. This is rate for the decay, and what we show in these papers is that actually turns out that processes like this one, for instance, scattering processes can also be different between process and conjugate process, right? You can have a comparison of these. The scattering rates for these need not be the same. That will also be a signal of CP violation. And we show that again you have to take tree level plus loop corrections in order to get any CP violation in. So you can cross these diagrams in order to get the scattering channels also. And we do all of those computations, and then we thermally average these rates, stick it into the right hand side of the Boltzmann equation and solve it, and generally show that you will get a baryon number which we start from 0 and then it builds up to something, and then whenever the expansion rate of the universe becomes bigger than this cross sections or interaction rates, you will have this thing reaching a terminal value. And this should be our BAU. And we show in the paper that there are regions in parameter space where you can get the observed BAU. Yeah? And because of this interaction, you can also have, so before I go to the next point, here we show that the mass of the chi, right, this new particle that we have added, can be over a very wide range. So we can get this to work all the way from 10 to the 4 GeV to very high scales. In this wide range, this thing can work. So what this does is to generate a net baryon number directly, right? And then we will have to say that, okay, the sphelerons convert some of that into lepton number. It's the other way around, right? So, and we just work out, solve the Boltzmann equation, show that it works for a very wide range of masses. And for the lighter of these masses, there is a chance that we can probe it in terrestrial experiments. Right, 10 to the 4 GeV, if we ever build some future colliders, right, we could test this kind of a process, whether, you know, like these quarks can give me some signals of this chi, there will be baryon number violation, and this is something beyond the standard model, right? You don't have any such perturbative processes that will show baryon number violation, and we can look for signals at colliders. Plus, right now there are experiments which are called as the neutron anti-neutron oscillation experiment. Super K has the best limits so far in this one, right? Because they look for neutron going into anti-neutron, and there is a limit on that. And future experiments are also planned. There is something called the European spallation source, which is being built right now, I believe. and they will also look for improving the bounds or looking for a positive signal in NN bar if an N neutron can oscillate into an anti-neutron. So why does that happen? So you start with something here which has the quantum numbers of a neutron, let's say UDD, and I can look at the sky, right? And so here is a neutron which is coming in, but the chi is Majoranoid, breaks fermion number, so I can turn it into the other kind in some sense, and then go into the conjugate, which has now, this was the quantum numbers of a neutron, and this has the quantum numbers of an antineutron. So what this a signal of this theory is the presence of neutron-antineutron oscillation. And if we find any such thing, it will give you credence for such theories. There are other things along similar lines. Generally, one thinks of it, this is called a neutron portal, for new physics. So there are many such models that have been analyzed, but what we did is to look at, this one is a vector interaction, it has a gamma mu in it. People usually look at scalar theories, but turned out that what we did was to look at vector theories. And so for further details, I'll just leave you to look at those papers. And I'll pretty much stop here about what I wanted to say. Last remark is that I did not get time to talk about every possible model out there about what generates baryon asymmetry. So there are like the earliest examples that were written down were what is called as a gut baryogenesis, right? In gut theories also you have baryon number violation and lepton number violation. So there are examples where in gut theories you can generate them. I didn't have time to talk about what is called as this Affleck-Dine baryogenesis, which there the proposal is that in supersymmetric theories you can have some flat directions, and they showed when such a situation happens that can help you in generating baryon asymmetry. There are many possibilities for this, and which one is realized, if any of them, only experiment can tell us. And so we have to keep searching, probing, and see if any one of them can be found to be true. Yeah. So any questions about this one?
So you showed the plot of this NBT with function of time.
Yeah.
So here you take the expansion parameter scale factor.
Yeah.
It is in the radiation dominated phase
Yeah.
or something.
Yeah. This is all in the radiation dominated epoch. Yeah. Yeah. That is only to convert between lepton number and baryon number. Yeah. Otherwise, they are not doing any generation of net baryon number or lepton number. They are just converting from lepton number to baryon number or vice versa.
No, in your direct baryogenesis, but then
Yeah.
you're saying you won't have atoms, is it? If you just have baryon number and no electrons, is it, to go with it? I mean,
That's right.
okay, I see.
Yeah, if something doesn't convert the baryon number to lepton number, then you will have no net leptons present. Right. I think that's a true statement, but yeah, we can think about it. Because lepton number 0 could mean still that you have electrons and then compensate in antineutrinos. If you have equal number of electrons and antineutrinos, you still have a net lepton number of 0. But you still need an excess of electrons over positrons. So how did that come about, right? Without some physics doing that, it's not easy to see why that would be the situation. Otherwise, you'll end up with this kind of a situation, all of them being equal is the most natural, and then when they annihilate away, they will all go away, and you have no electrons or positrons, and that would be the most natural situation. In principle, you could contemplate something did that, and sphellaron is one example which will give you that, right? It will generate a net lepton number, which is, I want in the end for electrons to be present, as you rightly said, that we must have electrons being equal to protons. Otherwise, we don't have a charge neutral universe. And that will happen automatically, right? Because electromagnetism is always conserved exactly in all of these theories. So you will be guaranteed that in the end, if you have one proton, you will have one electron by just construction. How it comes about is maybe to trace it is a bit complicated. Like the sphelarons are doing a pretty non-trivial thing, but always keeping electromagnetism intact, right? So in some way, then if you end up with a net proton number, you must have somewhere or the other created electrons. Otherwise, you will end up with no net proton number. That's the other way of solving that problem, but then that's not good for us. So we need to invoke some mechanism where you have a net proton number, and that mechanism should automatically then create equal number of electrons. And sphelarons is one thing that will do it.
Slightly different, digressing a bit. So I have heard of there are some kinds of models which modify the Higgs, the potential, the Higgs self-couplings.
That's right.
Which could induce some strong first-order electroweak
That's right.
phase transition, which
Yeah.
in turn could also induce baryogenesis.
That's right.
Could you comment on
That was the first 10 minutes of my lecture.
Oh, yes.
So that I just very hand-waving way pointed out that coupling, one example is in supersymmetry, the right-handed stop. It's like, I know people have worked this out and shown that, that can lead to, you compute the effective potentials with new particles coupled to the Higgs and show that it can be of the first order phase transition type. And if you can invoke a new physics which will modify the Higgs effective potential in order to give you a first order phase transition, then you have bubble nucleation, and the bubble wall, when it is expanding into the false vacuum, will give you an out of equilibrium situation where there is a net current of lepton number or baryon number into the bubble wall, and the reflection coefficients and transmission coefficients are different, and if you have CP violation, then the amount of leptons going through versus amount of anti-leptons going through can be different, and so you have out of equilibrium condition and you have CP violation, which is then giving you a possibility of an asymmetric transmission coefficient. And then when things go into the bubble, into the true vacuum, because the sphelarons are not active there, they get frozen in. And so then the bubble expands and fill our entire Hubble volume, and we will have a net asymmetry which is not wiped out, because inside the sphelarons are very, very suppressed. And so you lock in all of that lepton and baryon number. And that's generally the situation in these models, where you modify the Higgs potential in order to give you a first order phase transition. And I pointed out this reference of Cohen, Kaplan, and Nelson. That's somewhere in the 90s, I believe.
Thanks.